Good evening, everybody, and welcome to Bristol Talks Economics. Tonight, we're delighted to be joined by Stephanie von Hinke, a Professor of Economics here at Bristol, and also a Professor of Health Economics at the Erasmus University Rotterdam. Thank you for joining our series, Stephanie.
Thank you. Thanks for inviting me.
Tonight, the format, we're hoping to get on to Stephanie's exciting research grant with the European Research Council. But before that, we're going to take it nice and slow because I know a lot of those in the audience, myself included, might not have much knowledge of genetics beyond designer babies at GCSE. So it'd be good to take it right from the beginning. To get the ball rolling, I'd just like to take it right back to the beginning and ask Stephanie, how and why did you become interested in genetics? And specifically, why did you choose to take an economic approach to genetics?
Well, I guess to sort of introduce, so I never really did an undergraduate in economics. My undergraduate was in health policy and management. But then my thesis in the last year, I wanted to do something quantitative, and the person I was working with suggested that if you're really interested in this type of thing, you need to go do health economics. So I did health economics and I went to York, and then I sort of just got really excited about the different things within health economics and in particular sort of the approaches that economists use to causal inference. So that's really what sort of got me going in this. So I decided to do a PhD, and actually I did a PhD in Bristol as well. And part of my PhD, I started to think about using genetics within the PhD to sort of try, initially just for identification. And I've always been interested in genetics. I remember from school, from my biology classes, that I always liked the science behind it and how it really worked and how, yeah, just the whole idea behind how, you know, people procreate and the DNA and how it all sort of fits together. So I always was really interested in that. So I started sort of thinking about using it within the work, obviously with collaborators, my supervisors at the time, but also with people in social and community medicine in Bristol. So there's a big group that uses genetic variation within epidemiology. So we started working together, and initially we were using genetic variation as instrumental variables, which I can talk about in a little bit. And I started doing that within economics. What we realize is it's economists are quite different from sort of people in genetic epidemiology or in medicine in that sense. And they were very critical of what we did. So I guess, so we're still sort of doing this work, but we're also sort of using a different angle to incorporating genetics within work, but I can talk a little bit about that in a bit. But that's sort of how I got here.
Yep, so you talked a lot about genetics there, so can we just have a quick whistle-stop tour for those of us who are probably not a bit rusty on it? If you could just give us a little bit of background about genetics, sort of the intuition we need to understand your research.
Yeah, sure. So, so basically what we use is molecular genetic information. So if we look at the human genome, basically the human genome consists of this double helix of DNA, so the two intertwined strands of DNA. And these strands, basically, they're made up of millions of letters. I don't know if you remember from biology, but they're basically the letters A, T, C, and G. And so the DNA is basically these intertwined strands of DNA with all these letters, and sort of stretches of these letters are called genes, and particular stretches that code for particular proteins, they're called genes. Now, if we compare any two unrelated individuals, if we compare their genetics, they're basically the same for over 99%. And just the less than 1% of the DNA that differs between individuals, they're called polymorphisms. And the most common studied form of a polymorphism is called a SNP, SNP. It's sometimes it's abbreviated as, it's a single nucleotide polymorphism, but basically we refer to it as a SNP. And it's just this one letter change. So rather than having, say, ATC, you would have AAC or ACC, for example. So it's just a one-letter change. And these differences between individuals are the differences that basically lead to changes in people's hair color, eye color, but also in people's behavior, in their education, in various traits that we can measure in observational studies. So to actually identify which SNPs are predictive of these different outcomes, the way they do that in medicine, but also in genetics, is by running a whole series of regressions. So just OLS regressions. It's the way they do it. It's called a genome-wide association study, or a GWAS. And it's basically millions of regressions that they run with different SNPs, which each of these SNPs where you have variation in the population. And they just look at which SNPs associate with an outcome, like education or cognition or height or weight or smoking or BMI or whatever. And what we know from these studies is that all of these traits that we're interested in as social scientists, but also a lot of traits in medical, in the medical field, they're what they call polygenic. And it just means that there's no sort of SNP for height or SNP for weight or education, but instead there are millions of SNPs that all explain a very small amount of variation in height or in education or in cognition or whatever. But what we can do is that we can either use these individual SNPs within social science or economics research, or what we can do is to basically create a score of all these SNPs. We call it a polygenic score. That basically it's like a weighted sum of each of these individual SNPs, of these millions of SNPs, that measures, in a sense, the sort of genetic predisposition or the genetic endowment towards that trait. So it would measure, that's at least how you could interpret it. So the genetic endowment for education, for example. So those are the sort of things that I'm talking about. So it's either an individual SNP or a score that summarizes your genetic predisposition towards a certain trait.
It's worth saying, I think that this is something that's only really come online since the 2000s, 1990s is when the genetic revolution really started. Can you talk about sort of what the technological changes that have enabled you to do this research?
Yeah, so there's been a lot of changes since then. First of all, there's obviously the technological advances in mapping the genome. There are different chips being developed all the time that are allowing you to be sort of more specific, more precise in the SNPs, in how many SNPs it covers. And I think a very big component here is just the cost. The cost has changed dramatically. It's reduced dramatically over the years. You can now probably genotype individuals for like £50 or probably even less. So you collect the swabs and then you send it off and it's a genotype individual. So the cost obviously has reduced a lot. With that, sample sizes have increased, which is really important because what I said about these genome-wide association studies, they basically, they regress a particular trait on these millions of SNPs, but you need really large samples to identify these very small effect sizes. But with this revolution or these changes that happened over the last 20, 30 years, there are more and more medical, but also social science data sets that have this information that you can create these consortia that put all these data together, and you create these to do these GWAS based on lots of different cohorts from different areas in the world, from different countries. So increasing the sample size available, and also being able to cover not just sort of medical traits that we might be interested in, like cancer or blood pressure or whatever, or heart disease, but also these social science traits. One other thing that I think is really important, that a lot of social science data sets, or some social science data sets, I must say, currently make these polygenic scores freely available online. So you could, like for the HRS, the Health and Retirement Survey in the US, you can download obviously the data after the standard registering, etc. But you can also download polygenic scores. So this data is becoming available and people start to use it. So there's more and more people using these data nowadays.
Yeah, I think for economics students, potentially those more interested in finance might be aware of the company 23andMe, which is going to go public through an IPO process this year, valued at billions of dollars. And again, that's exactly what you're talking about, with a quick, easy polygenic score, which can then tell you if you're more likely predisposed towards the BRCA1 breast cancer gene, for example, and that is really changing.
Yes, yeah. So 23andMe is a big company. There are lots of other companies as well, and Yeah, I know lots of people who have been doing their swabs, sending it in, and also because they link. You see all these messages on in the newspaper, right, where they find long lost relatives that they didn't know they had, but also they have all these stories that they find actually that their father is not their father, and it could it could lead to quite a few issues as well. But yeah, there are lots of these different companies that are sort of really exploiting the fact that this is really booming, this industry, and people are more and more interested in their heritage and where they're coming from.
Mm-hmm. And then moving a bit closer towards some of your current research, could you maybe outline in broad terms the sort of classical pop culture nature versus nurture debate and where you sort of come into that?
Yeah, so if we think about sort of genome, so that sort of links to the gene-environment interaction. So that's this is this sort of debate on nature versus nurture. So should we be, are our outcomes shaped by people's genetics, your nature, or is it really the circumstances that we grow up in, or the environment that we grow up in? And this debate has been going on for hundreds of years, and much more recently, it's people start. I think the consensus, really, what we can say now is that behavior or outcomes and behaviors are really shaped by both. So it's this interplay between genes as well as environment. So not just your genetics, but also where you grow up and how and in the environment that you grow up is all going to be very important. So in terms of this sort of G by E research is not new. It's been done for years, this research, looking at sort of whether particular environment, the effect of a particular environment is higher or lower for those with a particular gene who carry a particular genetic variant, for example, or for those with a high and low polygenic score, or the other way around, whether a particular polygenic score is more important in certain environments. Like if you grow up in a wealthy environment or maybe in poverty, the effect of your polygenic score may differ. So this has been done a lot, but I think what economics and what particular economics can bring here is the methods that we use. So this focus on causal inference, this idea that these environments, they're not random. We choose our environments, we select. We select on where we want to live and what we want to do, and those selections are partially based on our genetics, and partially they might also, some of it might be random, but we select our environments. So by just using a particular environment and interacting it with genetics, we don't necessarily know what it's picking up. Is it really an environmental effect, or is it partially capturing your genetics? So what I think this molecular genetic data can help is, say we're looking at sort of the government introduces some sort of policy. So, and we can have two groups where, one is exposed, so a treatment group and a control group, if you like. That's how we refer to them. So we're one who's exposed to this policy and one who's not, but they're comparable. So we can sort of help understand whether there is any variation in the policy responses across individuals. So say whether those with a high polygenic score for a particular trait respond differently from those with a low polygenic score. And assuming that we have sort of exogenous change in this policy, we could say a little bit more about causal G by E. So I can give some examples if that's useful. I mean, it might be a bit abstract still.
There's a great example you gave just when we were talking before we came live about people with a tendency to be alcoholics. Could you maybe present that as that?
Yes. Well, it's not actually a tendency to be alcoholics, because I think the important thing, I think, with these SNPs and with the polygenic scores is that they change your behavior, but they don't make you an alcoholic. But they basically are associated with slightly more drinking of alcohol. So, for example, there is this is based on the polygenic score for alcohol consumption. And this paper that I just wanted to mention is by Biroli and Soon from the University of Zurich. And what they do is that they have basically a polygenic score for alcohol. So those with a high polygenic score for alcohol are more likely to drink compared to those with a low polygenic score. And conditional on drinking, they drink more. So what they do in their paper is that first they look at where they want to look at the proximity to pubs, basically. So first what they do is, where do these people live? And they find that individuals with high polygenic score for drinking, they live closer to pubs. And also when people move, so they have their date of birth and where they live now, and there's a correlation with those with a higher polygenic score, they are moving closer to pubs compared to where they lived beforehand. So there is a clear selection. This is what we talked about earlier. There's this selection in where do people move to based on their genetics. There are obviously other important determinants of where you're going to move to, but one of these things, what they find in the data, is that it's basically also related to your genetic predisposition for alcohol. And then the other thing that they look at in this paper is where they look at the licensing laws that have been introduced. So they look at where basically you make alcohol more restrictive. It's harder to be able to access alcohol. And they find that those with a high polygenic score for alcohol, so those who drink more, are less responsive to these policies. So they might reduce their alcohol a little bit, but not as much compared to those with a lower polygenic score for alcohol. So you get these genetic heterogeneity in responses.
Yeah, and that has serious policy implications, I guess. So the key point then for us who don't understand genetics as much is that genetics are probabilistic rather than deterministic, right?
Yes, yeah, clearly, yes. If you carry a specific genetic variant, it doesn't mean that you're also going to develop whatever symptoms or whatever disease is associated with that. There's clearly a probability, and actually looking at individual prediction currently is really hard. There are cases where it's being used, and for some cases there might be a better, it might be more possible to do that, but in a lot of cases individual prediction is just not sufficiently predictive to if we look, for example, at the polygenic score for education, it explains a large amount of the variation. So 11 to 13% of the variation in education we can explain using a polygenic score, so just based on genetics, which is really, really large. But actually we can't predict whether individuals are going to be higher educated or not, and whether they need additional treatment if they're not. So individual prediction, I don't think we're anywhere near that, and I doubt whether we ever will. But it's in some cases perhaps we are.
There's a really fascinating example of this. You've seen this one. It was about Mike Tyson and Mike Tyson's brother Rodney, where Mike Tyson's brother Rodney is a surgeon.
Okay.
So obviously Mike Tyson was arrested 38 times before he was a teenager, and Rodney spent his entire life helping people, saving lives. But clearly they share at least 50% of their genetics.
Yeah.
And probably grew up in a similar rough environment. But then the question is, does that bring in Robert Plomin's idea of non-shared environment factors, whereby these sort of there's contingency, idiosyncrasies in life that then determine what you end up. And I think that links to sort of the educational outcomes. There's a genetic element, but there's a lot of just idiosyncrasies that we just can't measure. Definitely,
absolutely. I think there are so many things that obviously we don't measure, we're not able to measure. Also, with the genetics now, we have the common variants. There are still sort of rare variants that we don't even measure, and they might also have effects. They might even have very large effects. But having said that, there is still, even though we can currently explain 11 to 13% of the variation in education, there is still 87 to 89% that we haven't explained. And clearly the environment is going to be crucial. So genetics is important. So in the example that you just mentioned, you have the brothers, one of them doing really well, the other one perhaps less so. They come from the same environment. They probably grow up in the same environment. They have 50% shared of genes, but still there are so many other things that that differ between these brothers. And it accounts for a lot of the variation. So it highlights this thing that it's really hard to do individual prediction with just genetics.
Yeah, but I think your research with the European Research Council is hopefully going to dig into that causality a bit more and try and figure out a couple more percentage points perhaps. Could you maybe outline, again in broad terms, what this big research project is and what the impact of that could be in the future?
Yes, for the ERC proposal, what we're doing with colleagues at Bristol, and I must say a lot of this research is not just with people at Bristol, so I'm collaborating with people at Erasmus University and Zurich University and also outside, but it's very much collaborative work. And what we're doing is, for the ERC proposal, we're mainly looking at sort of very early life environments. So we're looking at, we know when people are born. The particular data that we use is sort of the UK Biobank. It's a data set in the UK where we have about 500,000 individuals. They're all genotyped. And the only thing we know about birth is when they're born. We don't really know much else. So what we're doing is to digitize information about the environment at birth and merge it into the biobank, and then looking at the later life consequences of early life, maybe adverse environments, where we look at different types of environments. So we have nutritional environments, we have sort of toxicological environments, so pollution, for example. How does being exposed to pollution very early in life, how does it affect your later life health? Economic environments like unemployment, if the local area has a sort of an unemployment shock, does it affect your health later in life and your education, for example, later in life? And also health environment. So if you're exposed to a lot of disease very early in life, does it affect your later life health and education? And the idea here again is to sort of exploit these exogenous changes in the environment. So looking at sudden changes, say in unemployment rates or in pollution or in whatever, sudden changes that we can, because of that, we can sort of identify these causal effects of the environmental influences, and seeing how individuals with a high genetic predisposition or endowment for particular traits respond differently from those with a lower genetic predisposition. So this project really focuses on the early life environment, whereas the projects that we're doing with collaborators at Erasmus and Zurich focus sort of on basically looking at the life cycle, so not just early life but also later life environments.
I think it was David Barker in the 1980s who sort of developed this approach to developmental origins of health and disease, which is something you're basically looking at. So could you maybe, if you could explain his what exogenous variation he exploited, because I think that's a really illuminating example.
Yeah, so he is, a pioneer in this. It's fascinating what he's done. He's done so much work, and he really highlighted. He's not the only one, but he's one of the ones who's really highlighted the importance of the early life environment. The fact that really your environment, not just often people thought that like the placenta would be this perfect barrier, and anything that the mother would drink or eat, it would not pass the placenta, so for the baby in the womb. What we know now is actually that a lot of things pass the placenta, like alcohol, like pollution, a lot of things pass, smoking, etc. It harms the baby potentially. So David Barker was one of the first to highlight these things, to that, basically arguing that the early life environment is very important for later life health. So one of the things that he's done in a paper with Osmond, was where they look at early life infant mortality rates. So they have data on infant mortality rates in the 1910s and 20s, I think, and they look at they also have cardiovascular outcomes in the 1970s and 80s. And they basically look at regional correlations. So regions that had high infant mortality rates are the same regions that had high mortality from cardiovascular disease. So the way they interpret it is that these infant mortality rates are sort of proxies for nutrition. They sort of, in a way, they proxy nutrition early in life, in utero, and in the first couple of years of life. And those circumstances lead to development of disease later in life. So we're working on something now where we sort of try and replicate that, and then we bring in the genetics as well to see again whether those with, say, a high polygenic score for heart disease, whether they are more likely to develop disease compared to those with a lower polygenic score, a lower genetic predisposition for heart disease, given these early life circumstances of infant mortality rates.
Yeah, that was just so fascinating to me, the fact that I think I was reading that they think that obesity could be essentially a pediatric disease based on what you've inherited and sort of like the environment, or the insults, I think, as they call it, when you were in utero. That's amazing. Could you maybe delve a little bit more into the science of how does that work? How can that possibly be?
Yeah, so they're different. So one of the hypotheses is that basically in utero, if you are exposed to insufficient nutrition in utero, there is a hypothesis that it sort of programs the fetus. So if you're, as a baby in the mother's tummy, you don't get enough nutrition, there is this hypothesis that it programs the body that when you come out, it's sort of, sorry, it's my background noise, I think. So when the baby comes out, it's sort of programmed to live in an environment with little nutrition. So if it then suddenly it's born and suddenly there is a lot of nutrition available, then people there might be sort of longer term consequences in terms of how their body develops, in terms of their weight later in life, etc. So that's one of the hypotheses of why, and it's called the fetal programming hypothesis. It's how like the fetus is programmed based on the early life environment in the womb, but also slightly after birth.
Yeah, that's really interesting, because when I was reading Robert Plomin's sort of very genetic heavy influence on outcomes for children, I was thinking this really takes the pressure off parents. But then perhaps this sort of focus on what happens when you're in the womb, etc., in your first life, that sort of puts the pressure back on parents, does it?
Yes, I think a lot of it is sort of, it does put the pressure back on parents. So there's also so sort of some of it. There is this study which I think is really interesting, that basically looks at, so is it okay with my background noise?
Yeah, it's fine.
Yeah, okay. So there's a study that basically looks at we inherit like 50% of our genes from our mother and 50% from our father. So 50% of our mother's genes we haven't inherited, and 50% of our father's genes we haven't actually inherited, but we could have done if we had randomly allocated them. But there's this study that basically creates a polygenic score of the 50% that you didn't inherit from your parents. And it shows that polygenic score also affects your the children's outcomes in terms of education. So the polygenic score for education of the SNPs that you didn't inherit, well, that just basically indicates that if these untransmitted genes affect your education, it must be that the parent is creating an environment that is that encourages or that incentivizes that education. So maybe the parents have more books in the house, and they're making sure that all the resources are available. So that it's basically, so your in that sense, your genetic predisposition sort of partially captures the environment that the parents are creating.
So that'd be an example perhaps of the nature of nurture and the selection effect, because
No, exactly. It's like the genetics, they sort of capture your genetics, that's true, but they also capture other things, in the sense that in what I just said. So you basically, your genetics, they sort of partially capture the environment that your parents have created for you, and that in turn is also that nourishes, or that sort of encourages educational attainment in the offspring. So there are sort of ways of trying to deal with that empirically, but it makes it much harder. So it's important to really understand what does a polygenic score really capture, and how do we interpret it.
Just sticking with the theme of children and early life just for a second. I know you're struggling with the background noise. Emily Oster is an economist who's also taken a very data-driven approach to this kind of stuff, and she's sort of found that previous research sort of overblown the impact of drinking coffee, drinking alcohol during a pregnancy. Do you have any thoughts on her research? How does that link to yours at all?
Yes, I think it's really interesting. I've read her book, and I really like it. I think it's a great book. I really like the fact that she bases all of, basically she's looked at the literature and also not just read it, but also sort of looked at it critically to see, do we really believe the assumptions that are made in each of these studies? For a lot of the things, I completely agree with what she's done. I think for the alcohol one, maybe I'm biased, and maybe obviously because of my own work. So we looked at the alcohol at sort of alcohol consumption in pregnancy, and how it affects kids' outcomes later in life. So looking at the educational outcomes at age of 7 or I think 7 to 16 or so. So if we look at the literature on this, basically there is some literature. There is currently, I think there are a couple of papers in more economics journals that try explore like policy changes or something that allows us to look at exogenous, to somehow exploit exogenous variation in alcohol exposure. But there's very, very little. And thinking about it, that you generally, if there is in a particular area, if there's little information and it's an area of importance in sort of medical field, they will run randomized controlled trials. But here you can't do it. You can't randomize some mothers to drink and other mothers not to drink when they're pregnant and just see what happens to their babies. So this is like a case where there is just very little evidence, so it's much harder to make these causal inferences. So what we did in the paper, which is like also using genetic information here, but it's using it in a slightly different way. So we're using it as instrumental variables. So this is in an IV setup. I guess most of you would have, well, at least some of you would have heard about this in econometrics. So it's basically a method that allows you to make some sort of causal inferences. So thinking about, say, what we're interested in this case, we're interested in what's the effect of drinking or being exposed to alcohol in utero, so in the womb, on your later life educational outcomes, so your key stage test scores. But drinking is endogenous, right? So mothers who drink are probably very different from mothers who don't drink. So we can't just compare mothers who drink and compare mothers who don't drink. But we actually do that in the paper, and we find that mothers who drink wine, their children do really well, and mothers who drink beer, their kids do not very good. But then if we look at who actually drinks wine and who drinks beer, it's the higher social classes, they drink wine, and the lower social classes, the unemployed, those with mental health issues, they drink beer. So it's just a selection what we're picking up there. So what we do in this, in that particular paper, is that we look at, we use a SNP in a particular gene, and the gene is called ADH1B, and we know from that gene that it helps in breaking down the alcohol in your body. So when you drink a glass of wine, ADH1B is one of the SNPs or one of the genes that helps to break down that alcohol. So if you carry a particular rare variant of ADH1B, it basically reduces your alcohol levels quicker than if you don't carry that variant. But what that also means is your alcohol levels go down, but this alcohol is basically metabolized into something called acetaldehyde. And acetaldehyde is not very nice. If that builds up quickly in your body, you'll get sort of facial flushes, you'll increase heart rate, feel a bit nauseous. So for individuals who carry that rare variant, they will get sort of more side effects, if you like, from alcohol use, and therefore they drink less. So there's a clear relationship between those who carry the variant, they drink less alcohol. So it's not like, what I said earlier, it's not like, we have a difference between binge drinking and not drinking. This is like the difference. I think what we find in this paper is about 0.6 of a glass per week. It's not very large. It's a small difference, but there is a clear difference in alcohol consumption. So we use this instrument. So this SNP this is only one SNP that we use as an instrument for drinking, and we look at whether it affects a kid's outcome. So we find sort of strong evidence that drinking in utero reduces children's educational attainment, so their exam results later in life, and that's just based on this IV analysis. Obviously, with IV there are certain assumptions. I can go into detail, but I won't want to bore you too much. Certain assumptions that are really important, and especially when we think about using genetic variants, we need to think about them in a bit more detail and they're sort of slightly more subtle. But I think it's an interesting case. In particular, as I said earlier, you can't do randomized controlled trials with this. So this is it just provides a different way of looking at this question. There will be other issues with this, and there are other issues with this sort of identification, but it provides a different approach to looking at this particular research question that you can't necessarily look at using randomized trials or just observational data. You can't just control for the relevant covariates because there will be a lot that we just don't observe.
Yeah, but thinking back to my second year econometrics, this is very good, because this is, you're trying to remove reverse causation, you're trying to remove endogeneity from emitted variable bias. So there's just basically you're trying to find a variable that is correlated with it but doesn't cause an emitted variable bias. Cool. So I think we're going to move to some more policy focus now, so the policy focus of your research. We've had some good questions already from the audience. So Anna's asking, this goes back to what you were saying earlier, about are there ways that economists / policymakers can respond to genetic-based heterogeneity?
Yes, I think that's a really good question. And I think they can. I think there's always this issue with genetics that, there's always this background of eugenics. We don't want to go there. We don't want to go there again. So there's always this thing, do we really want policymakers to get access to our genetic data? But I think in most cases, that's not even necessary. And I think policymakers can use this genetic information. So one way is obviously, with this this instrumental variables that I just mentioned, where you can try and find sort of the causal effect of, say, drinking on kids' outcomes, that obviously has policy implications. But even when we think about sort of gene-environment interactions, so say whether a particular environment, the effect of an environment is worse for those with high versus low genetic predisposition, even then I think there are policy implications. For example, say the government has two options of, they want to increase kids' attainment in schools, kids' exam results, and they have two options. So say they can use smaller class sizes, or perhaps, I don't know, more teachers in the class. And if we know from the literature that both of those increase kids' attainment, for example, I'm not saying it does, but assume that both of these policies, if you like, they would increase educational attainment among kids. But actually one of them, we know, perhaps if we do a study on that, we know what we might find is that maybe having more teachers in the class would actually increase genetic heterogeneity in attainment, in that perhaps those with a high polygenic score would benefit more from these additional teachers compared to those with a low polygenic score. Whereas maybe if we think about class sizes, perhaps what we might find is that smaller class sizes benefit those with a low polygenic score for education much more than those with a higher polygenic score. So it would reduce genetic inequality within children or within the population. So if there are these sort of two potential policies, say, that the government might be considering, then looking at the evidence on G by E, even that, it might help in sort of, what do we want as a government? If obviously there are other factors that play a role, like cost, but say everything else is constant, then perhaps what you might want to choose is the policy that would reduce genetic inequality rather than the one that would widen it even further. So in a sense, I think there is scope for policy, to take that into account within sort of within the policies that they might, the policymakers or whatever they might want to introduce.
So that's really interesting, because as I understood it, there was ways that you can reduce inequality of opportunity, but it's hard to reduce inequality of outcome because you have these genetic differences. But what you're saying there is you actually can reduce the genetic inequality. Yes, in a sense. I mean, obviously your genes you can't change. They are fixed at conception. They're not going to change over time. The only thing we can do is to change the environment. So if there are environments that would basically eliminate any genetic difference, inequality or differences between individuals, that in the particular environment, whether you have a high or low polygenic score for education, it just doesn't matter anymore, then that would be preferable, because being able to, the environment we can change. So if we can identify an environment where there are no genetic differences between individuals, or at least we reduce them, then that would obviously that would be preferred, and that would improve the outcomes, at least across the population. Okay, so Sabri has asked, I think, two related questions. I'll put them to you together. Is there a polygenic score correlated with IQ? If so, does the regression become weaker for higher IQs? And then are polygenic scores associated with positive outcomes becoming more equal? If so, is this expected to continue or reverse? Sorry, I'm going to open the chat as well. So, where is it? I'm hoping you can understand that better than I can. Is there a polygenic score correlated with IQ? If so, does the regression become weaker for higher IQ? What regression? So IQ on polygenic score? I don't. So there is a polygenic score for IQ. Well, not IQ. There is a polygenic score for cognition.
So there is a score for cognition. There is also there are also scores for sort of non-cognitive skills. So they've done like genome-wide association studies for non-cognitive, so like the big five, for example. So there are sort of genetic determinants of like the big five cognitive scores, etc. I'm not quite, I don't think I understand. Oh, there. Does the polygenic score do less well at predicting IQ at higher levels of IQ? So generally, the polygenic score is basically a linear prediction of your outcome, in this case IQ. So it doesn't do less well at high or low IQ. It's basically the way it's created, because it's a weighted sum of all the individual SNPs, weighted by the strength of each of the SNPs in the GWAS. So sorry about all the detail, but it's basically a weighted sum of these individual SNPs. So it's the best linear prediction of the outcome that we're looking at. So it doesn't, it's not sort of less well at predicting IQ at higher levels. So yeah. So I don't. Yeah. So there is this polygenic score, and I haven't read that it sort of performs less well at other levels. I think it's just a linear prediction.
And then there's also Anna's question there, which I think is going into the interdisciplinary nature of your work. Do you think rather than economics being a new way of looking at medical issues, biology can feed back into economics? Yes, definitely, absolutely. I think that's really important, and that's what I like so much about this. You know, we're learning so much from what they do in genetics, what they do in medicine, in behavioral genetics, all these ideas that they have been using for years and we just don't know about. That's what we're trying to incorporate within our research and within economics, and see whether we as economists can learn something about that, and whether we can incorporate that in our research to make it richer and to make it also perhaps more representative of the world. You know, we're coming into this as a new field, and this is such a vast moving field where things are going so quickly. We're looking at, you know, different literatures, genetics literature, the medical literature, the behavioral genetics literature. So all these literatures are going very quickly. So and we learn so much from sort of trying to incorporate what they do in these different areas into our own research. And it also goes the other way around. So for example, this idea of using genes as instruments, this is very popular in social medicine or social genetic epidemiology. So there's a group in Bristol in the integrative epidemiology unit in the School for Social and Community Medicine, where they do a lot of using genetics as instrumental variables. So they call it Mendelian randomization. But and the interesting thing is so before any of this, they didn't use instrumental variables very much, or maybe at all. But this has basically, they are now sort of developing new methods on how to use IV and different ways of using IV, or very much sort of within the framework of this using genes as instruments. So sometimes you might have, you know, thousands of instruments as opposed to just one. Like in economics, we're always, you know, we're happy if we find one, but here they might have 1,000 genes, so they have 1,000 instruments. So they develop these methods at a much quicker pace now there than I guess what we do in economics, but all very much specific to that application. But I think it goes in both ways. We learn a lot from what they do in their areas, and we try and incorporate it within our work. And obviously, hopefully, what we do, at least what we're sort of good at in terms of, you know, the methods or the toolkit that we use in economics and econometrics, some of it is also being used in other areas. And sort of coming back, you know, to the question by Anna, also other areas like neuroscience, I think it's fascinating. You know, there are some economists also that I know that are looking at MRI scans and incorporating the information from MRI scans within economics in a way. And I think, again, I think it's fascinating. I'd love to do more of that, and to sort of just to learn more about, you know, what do they know in these areas, and how does that inform what we do in economics, and potentially what we do, how does that inform the way they think about these things. So I think I think we learn so much from the interdisciplinary area, that I think I just think it's fascinating to sort of, you know, understand a little bit from both worlds. Mm-hmm. I think Ollie would now like to move the conversation into interdisciplinary philosophical realm.
Oh, gosh.
What is your view on using genetic engineering, which may very well become possible in the not so distant future, to reduce genetic inequality?
That's a very difficult question. I just think we need to be so careful with any of that. You know, there are these Hans, there are these you know, this talk about designer babies, etc., and that's all, you know, based on genetic engineering, and in some cases this is possible, and currently, obviously, in most countries it's all not allowed, which is a good thing. But I think as soon as we let any genetic engineering, as soon as we allow for any of that, I think it's just a slippery slope. I don't know. I think we just need a much more, you know, again, there are other, like, we need a better legal framework. I think maybe we already have it. I just don't know. I don't know much about, you know, the legal side behind this. But there clearly needs to be a lot of a legal framework for this, and what do we do? How do we deal with these cases? I think that's it's a really difficult question, and I don't think I'm in a position really to answer it. I think it's a very interesting question and a very relevant question, but yeah, it's very hard. And I think we just need, we need people in lots of different fields to think together, and also just the views of the population. What does the population want? From what I've read so far, which is obviously not a lot, but I think people are not very keen on genetic engineering, but maybe that also changes over time, who knows. But yeah, it's a very important question, but a difficult one as well.
Yeah, there seems to be two very distinct tracks we can go down. We can go down the Chinese version, where I think they're sequencing a lot of babies' genomes now. Obviously, no idea what they'll be using that for, but potentially monitoring purposes. Or there's the much more benign version of using this new genetic mapping, as we can work out, you're predisposed towards obesity or alcohol consumption. We can give you these steps now to lessen it and make it less likely that you'll suffer from these diseases in future. I think that's probably the positive aspect of it we need to emphasize.
Yes, no, definitely. And in some cases, I think it's very helpful that you can avoid any sort of big medical problems before they actually take shape. But there are papers that talk about that you can based on the polygenic score, again, say for education, that you can identify fetuses that have a low or in the bottom 25% of the polygenic score of education, and you think, and then, yeah, what do you want to do then? I don't know. I find it quite scary about what, you know, we don't select on that, but it's possible potentially. So we clearly do need to think about it, and we need to have clear guidelines and rules on this. But they will differ in different countries, and that'll probably always be the same. But it's a tricky area that I don't really do much about, but it's very interesting. Yeah. So yeah.
The immediate thing that springs to my mind is the fact that the US healthcare market is already pretty tricky. If everyone gets on 23andMe and then insurers can start having access to your polygenic scores, then there's a serious adverse selection problem there, isn't there?
Oh, very, absolutely. I think in a sense I don't know where this is going to, but currently I would be quite skeptical of the government getting access to any genetic data for individuals and linking it obviously to other records, and the same for insurance companies or other sort of private companies that could use them for their own profit or for their own good, as opposed to for the good of the individual. So in a sense, I think there are clear sort of ethical issues that we need to be thinking about. But at the moment, I don't really see any need for the government or for private companies to get information on this genetic data. So there are some cases where genetics is being used for individual treatment decisions, like should people be screened for cancer? It's normally, what is taken into account is like your family history and whether you smoke or something, some other characteristics. And now they additionally want to use like genetic predisposition for certain traits. So in those cases, it's being used, but even then, it's quite tricky because it basically relies on individual prediction, and that's really hard. For some traits, it might be better than for other traits, obviously, with traits that are where you have a much higher R squared, so a much higher, you explain more of the variation in that trait, you're probably better at predicting than, and obviously traits that have a small R square, low R squared, but still individual prediction is just really, really hard. But I think if that improves, I think there are other ways through which we can have sort of potential policy implications. Because so one of the things that I just mentioned is like, if we can identify children with like dyslexia earlier on, because of, based on polygenic scores, or maybe identify children with ADHD earlier on than when they are currently being diagnosed, we can help them in the education system and provide resources for them to be able to adapt and to teach them in the best way for them possible. So in that sense, I think there is another sort of potential policy application, but again, it depends on individual prediction again. And the other thing is, we, for example, with smoking, for example, we have these, one thing that the governments have been trying to do to get people to reduce smoking is to increase taxes. And tobacco taxes have increased dramatically over the last, 30, 40 years. And it has reduced smoking. I mean, the smoking numbers or proportions of the population, it's really gone down. So it is working, and that's obviously because of lots of different policies, not just tobacco taxes. But it is working. But there is still a group of individuals who just do not stop smoking. So they are just not susceptible to any policy, whether we are going to increase the price of cigarettes, by tenfold, they're not going to budge. So perhaps that just means that perhaps if we can identify with research that perhaps these people that don't respond are those who have a high polygenic score for smoking, they're just so addicted that whatever you throw at them, it's not going to work. So perhaps for these individuals, we need to be thinking of different treatments, like maybe more medical treatments, pharmacotherapeutic treatments, whatever. Perhaps by doing some of these analysis, we can sort of identify groups of individuals that simply, they don't respond to one particular treatment. Perhaps we should be thinking about a different type of treatment. And I think that's another way where policy potentially can come in. But again, it sort of does depend a bit on being able to identify that group, which might be hard.
That links, I think you did a fascinating paper about sort of the impact of people who smoke for weight loss. And so you're talking there about when you increase the price, and yeah, they're very inelastic in their demand for smoke. Could you explain to everyone about that? Because I think that's really interesting.
Well, it's a while ago. So what we do there, we looked at smoking. So I think there was a question in a particular data set. Why do you smoke? And one of the reasons was because I want to lose weight. So and actually this is a study in the US, but actually there were it's a long time ago, but from memory, there were quite a few people who actually reported that they were smoking just to lose weight. So we were, this is in a sense that, smoking, so you smoke not because you necessarily like the taste of it, but only to be able to lose weight. So it's just derived from the demand for weight loss. You want to lose weight, and because of that, you start smoking. So you build up that potentially addiction for cigarettes. So it's a bit strange. So we did that study a while ago using this American sample of I think it was 10 to 14-year-olds or something. But already there, you saw quite a lot of people who were smoking for the only reason being for weight loss. And yeah, it would be interesting to have sort of genetic information there to see, obviously we don't have a sort of an exogenous change in an environment, but just to see, are these also the people who then, if these are the people with a higher polygenic score for smoking, then they're probably more more easily addicted to smoking, and would be harder for them to stop smoking afterwards. But we didn't have any genetic information for that, but it would be nice to sort of be able to incorporate that in some of these issues.
And even if you could look at heritability in terms of body weight as well, you could see whether the people who are smoking, whether it's more effective for those who've inherited a tendency to have a higher BMI or whatever.
Exactly. Absolutely. I think that's another one. I think in general with I think there's one thing with these gene environment interaction studies that, we can create hundreds of polygenic scores and we can try them all out. And one of them is clearly, we expect 5 of the 100 to be significant at the 5% level, but we probably don't want to be doing that. So I think with these, gene environment interaction things, I think one thing that is useful is to sort of pre-specify, or at least have like a polygenic score that's predictive of either your outcome or your exposure, to sort of make sure that we don't sort of just try them all and see which one is significant, because that's a bit cheating.
We're coming towards the end now, so I was just thinking maybe you could give us, I know it's obviously a rapidly moving field, but where you think the next move in the field is going to be, perhaps your own research, somebody else's research, where the next big breakthrough is going to come, and where economics is going to play a role in that.
Yes, I think so. I think in terms of in economics, so there's one thing obviously that I think that gene environment interaction work is clearly going to increase, because partially, as I said, these scores are available in social science data sets. People are going to start using them. They might use them within G by E. They might simply use them as covariates. So one thing that you can do is to sort of just put them in as covariates to sort of mop up omitted variable bias, if you like, but to mop up any residual variation. So if you think about the sort of standard textbook example of like the returns to education, so you regress wages and education, what they always say is like ability is unobserved, right? So now actually, if we have genetic data, we can at least observe some of that ability. Clearly, we're not going to deal with all the omitted variable bias, but we could potentially do a bit of that. So that's one way of sort of incorporating genetics. I think as instruments, I think economists need to be convinced that they are valid instruments. To be honest, I think in some cases, I think there is reason to think that they could be valid. In a lot of other cases, I don't think they are, and there is a lot of evidence that probably they aren't. But I don't think that we can just simply, because in that case we could just ignore all of this literature. There's clearly a really strong literature, perhaps not in economics, but there's a really strong literature that uses these genetic variation as instruments, and is doing really well, and it's having impact, affecting policy, etc. So clearly, I think that's an area that economists need to be convinced, but it really depends on the application. One thing that I think this area is moving into is that we have data on family members. So we need family trios. So currently, most of the genome-wide association studies are done with individuals. We don't have any family information. Sometimes we might have siblings, but the samples are very small. And this thing that I mentioned earlier, where the not untransmitted SNPs also affect your outcomes, that is an issue that your SNPs are picking up environmental effects. So when we have family information, so either family trios or sibling samples, we can try and overcome some of those issues. And there are more and more samples being collected, more and more being done to try and get sort of family members with genetic data for both the child and the two parents, or just the two siblings, to be able to overcome some of these familial influences, if you like, the family environments that we need to sort of remove from the genetic score to ensure that we just capture in genetics. And then there are lots of applications that we can do. So I think it's such a fast moving field, but it's also a very exciting field to be in. And yeah, I look forward to seeing where everything's going to go. I mean, who knows?
Yeah, absolutely.
But,
I think that's a perfect place to leave it. So thank you so much for joining us, Stephanie. That was a fascinating introduction to genetics and economics, and maybe some of those listening tonight will go into the field in future and follow in your footsteps.
That would be lovely.
Thank you.
Send me an email, that'd be good. But thank you very much, Ben. That was great.
Thank you. Thank you to everyone for joining. We'll see you next week.